In this video, we are discussing the 11th question from the exercise for the chapter Laws of Motion, which is the fourth chapter for 11th standard physics. Now, as per the question, we have a ball of mass 100 grams, and this ball is dropped from a height of 5 meters onto the ground. Because of this, the ball will bounce repeatedly. Now, we have been told that during every bounce, the 64% of the potential energy, that is the energy before the collision, is converted into the kinetic energy, which is the energy after the collision with the ground. And using all this given information, we have to answer a bunch of different sub questions. So, सबसे पहले let's start with the diagram of the question. So here we have the ball at a height h, which is then let go, and because the ball is falling under gravitation, it will come down towards the ground. Once it hits the ground, it will bounce back, and then it will again attain a height beyond which it cannot go up. So now it will start falling towards the ground again, and again it will hit the ground, and again it will bounce, and so on. So for our question, we are required to observe the bounce of the ball for three bounces. So we have presented the three such bounces of the ball. One thing to note is all the speeds which are given in blue ink represents the speed with which our ball is approaching our ground, and all the speeds which are given in green ink or green color are the speeds with which our ball is separating from the ground. So this is the speed before the ball collides with the ground, and this is the speed after the ball collides with the ground. Now we'll keep on referring to this diagram from time to time, but first let's get into the solving process. सबसे पहले let us write the given data. And the first data that's been given to us in the statement 1 of the question is the mass of the ball as 100 grams. So we'll represent it into kg. So it becomes 0.1 or 10 raised to minus 1 kilograms. The second quantity that's been known to us is the height from which the ball was dropped, and that height is said to be 5 meters. So meters is already in SI unit, so no need for conversion. And the third given data is a statement. And as per the statement, the energies after the collision or after the bounce is 64% of the energies before it. So kinetic energy is 64% of the potential energy. And the first thing we need to calculate is the coefficient of restitution, represented by letter E. Now, as per the definition, we know coefficient of restitution is the ratio of separating velocities divided by the approaching velocities. And if our example was the first bounce, we can say it is a ratio of v1 by u1, as v1 is the speed with which the ball and the ground is separating, and u is the speed with which the ball approaches the ground. So with this, I can rearrange the terms, and I can say v1 is equal to minus of e into u, and let this be our equation number 1. Now, also, as per the given condition, we know that the kinetic energy after collision, so it becomes kinetic energy final, is 64% of the potential energy. Now, one thing to note is the potential energy that the ball had at this height h will start to convert into kinetic energy as it starts to fall. And right before the ball hits the ground, whatever kinetic energy, which is the kinetic energy before the collision, will be the result of the potential energy over here, which was converted. So I can say that this potential energy is nothing but initial gets converted into the initial kinetic energy, that is the kinetic energy with which the ball is approaching towards its collision with the ground. And now if I were to bring this term on the LHS, I would get kinetic energy F, which is the energy of the ball after colliding with the ground, and kinetic energy I, which is the kinetic energy of the ball before it collides with the ground. And that ratio is 64 upon 100 from the above. And from the definition of the kinetic energy, if I were to calculate kinetic energy after the ball collides, so it will be half m v1 square, as v1 is the speed of separation. And if I were to calculate the kinetic energy before the ball collides with the ground, it would be half m u square, as u is the speed of approaching. So from this, I can cancel half m and half m, which is the common term in numerator and denominator. So I get a resulting term as v1 square divided by u square is equal to 64 divided by 100. Now from equation 1, we can say v1 is equal to minus of e into u. And if I were to substitute that value of v1 over here, I would get minus of e into u raised to whole square divided by u square is equal to 64 upon 100 from equation 1. And if I were to open the bracket, I would get minus of e square is e square, u square is u square divided by u square upon 64 upon 100. From this, I can cancel the common term u square from numerator and denominator, which gives me e square as a ratio of 64 upon 100. And now, if I were to calculate e, I simply take the square root. From that, I get e is equal to 8 by 10 or 0.8, which is our value of the coefficient of the restitution. With this, our part A of the question is done. Now let us move on to the next part, that is to calculate the speed after the third bounce. So in our diagram, if we were to represent, it would be speed v3. So before we do that, we know that v1 is equal to minus of e into u. We just calculated this. And we also can calculate using the equations of straight line motion that u is equal to root of 2gh. So if you were to apply the equations of straight line equation for this particular instance, you would get the relationship between u and gravitational acceleration and height with which it was dropped from. So it is equal to u is equal to root of 2 under root 2 gh. And now, as we said, v1 is equal to minus of e into u, because e was given as minus of v1 upon u, where v1 was the speed of separation and u was the speed of approach. Similarly, for second bounce, the speed of separation would be v2 and the speed of approach would be v1. So we can say e is equal to minus v2 upon v1. So if we were to see, for second bounce, our v2 is the speed of separation and v1 is the speed of approach. Hence, I can say v2 is also equal to minus of e into v1. Now, if we were to substitute this value of v1 in place of v1 for v2, we would get a new expression for v2 as minus of e into u. So if we were to further calculate, we get v2 is equal to e square into u. Let this be our equation number 3. Now, as we did for second bounce, if we were to calculate for the third bounce, we can say v3 is equal to minus of e into v2, because in the third bounce, v3 is now the speed of separation and v2 is now the speed of approach. So we get an expression for v3 in terms of e, which is coefficient of restitution, and v2, which is the approaching speed in this case. Now, if we were to substitute this value of v2 for in this expression, we would get minus of e into e square into u. Therefore, v3 finally can be said as minus of e cube into u. This is the value of v3. Now, we know the value of e, but sadly we don't know the value of u. But we can substitute the value of u as root of 2 into gh, which we have already determined it as. So from 2, I can say u is equal to root of 2 gh. So v3 now becomes minus e cube into root of 2 gh. Now, in this particular term, we know the value of e, we know the value of g, and we also know the value of h. So if we were to substitute the values of respective terms, we would get e as 0.8 the whole cube into under root of 2 into g, which we have taken as 10, and h, which is given to us as 5. So if we were to solve this particular value, we would get v3 as minus of 5.12 meters per second. So this is the value of v3, that is the speed of the ball after third bounce, which we were required to calculate. With this, now let's move on to the next sub question of this numerical. Now, in the next part of the numerical, we need to calculate the impulse of the given ball during the third bounce. Now, as per the definition, impulse, denoted by letter J, is defined as the change in linear momentum, which is defined by letter P. So for third bounce, if we were to calculate this change, it would be momentum, final momentum, that is during the speed v3 minus the initial momentum, which was because of the speed v2. So I can say the change in momentum will be m into v3 minus m into v2. Now I can take m common from both these terms, term 1 and term 2. So I get resultant term as m into v3 minus v2. That makes an expression for our impulse. Now from the above calculations, if we were to substitute the value of v3 and v2, I can say v3 can be written as minus of e cube into u, and V2 can be written as E square into U from equation 3 and equation 4. Now from these two terms, that is term 1 and term 2, I can take the term minus E square into U as common. So if I were to do that, I would get the resultant term as minus M E square U into 1 plus E. And we know the values of all the terms over here, and if we were to substitute the values, we would get minus of M is substituted as 10 raised to minus 1, which is the given values. E square is substituted as 0.8 the whole square, as E's value we calculated is 0.8. We can calculate the value of U using the formula. We can substitute the values of G and H over here, and we get the value of U as 10. So value of U is 10, and then we know 1 plus E, which is again 0.8. And if we were to solve this further, we would get our impulse as minus of 1.52 Newton second, which is the unit of the impulse. And this was our part C of the numerical, that was to calculate impulse, which comes out to be minus 1.52 Newton second. With this, now let us move on to the next sub question of this numerical. Okay, so in the next sub question of the numerical, we are required to calculate the average force exerted by the ground. Now, we have been given an additional quantity for this sub question, and this quantity is the impact duration or time of impact, and it is given to us as 250 milliseconds, which if we convert it into seconds becomes 0.25 seconds. Now we have multiple formulas or ways to calculate force in physics, but as per the quantity that we know, that is we know time and we have already calculated impulse, we can use the definition of the impulse, as impulse is also said to be force into time. So we can say that from this particular formula, I can say force is equal to impulse divided by time. And we know the value of impulse as we have calculated previously, and we know the value of time as it's given to us. So if I were to substitute these values from the previous equations, I would get the value of force as minus 4.608 Newton. So we have just substituted the value of impulse and the value of time. 0.25 can be represented as 1 by 4, and if you were to solve this further, you would get force as minus 4.608 Newton. Let this be our equation 6. Now, after this, we have to calculate one more physical quantity, that is to calculate the pressure exerted by the ball. And for this, we have been given an additional given information, that is, we have been given the contact area of the ball, and it is said to be 0.5 centimeter square, which if we convert it into meter square, it would be 0.5 into 10 raised to minus 4 meter square. So now pressure formula as per the definition is pretty simple. Pressure is defined as force by area. So we know the value of force as we have just calculated it. We know the value of area as it is given to us. And if we were to substitute those values, we would get our pressure as 9.216 into 10 raised to 4 Newton per meter squared. So with this, we have solved all the sub question for the numerical number 11 from the exercise. If you want the PDF of the solution, do check out the description box. With this, I hope it helped you. Thank you.